Hello minions, hello we enthusiasts, welcome to session number 3 of Capacitors, where we are going to discuss about how a dielectric material placed inside the capacitor affects its capacitance and the energy considerations that you need to do. Also, we are going to discuss about the charging and the discharging effects of a capacitor. We are going to see those functions. We are going to see all those related equations related to charging as well as discharging and some really good problems towards the end. So stay tuned with me, Shreyas, your master teacher for physics at Vedantu. And remember, today's session is a premiere session. That means I might not be able to see your chats, but do not forget, you can always interact with each other, help each other, because we are a family. Remember that. And all the new members out here, welcome to this channel, We Enthuse. And this is Shreyas here. I'm the master teacher for physics and I teach on YouTube as well as the regular sessions at Vedantu. So I have been teaching for quite some time now, and with my experience, I know that how to train students, and I'm going to do that, and I'm going to make sure that you crack the JEE 2021 exam, or if you're an 11th standard student, then the JEE 22 exam. So welcome everyone. You can also follow me on my Instagram handle, that's Shreyas_Vedantu, where I keep posting all the regular updates, interesting videos and a lot of fun stuff. So please do follow me over there. Let's begin today's session without any further delay. And do not forget, if you're a new first time user out here, do not forget to subscribe to our channel, because only when you subscribe you will get all the important updates and the notification. And if you're already done that, then do not forget to smash that like button, because without your likes we are not going to get that energy. So go ahead, smash that like button, and only then we can proceed. All right, so let's begin today's session, and let's talk about first what happens when you put a dielectric inside a capacitance. If you have not seen one of my previous sessions where I have spoken about dielectrics, I urge you to do so before watching this session, or probably towards the end of the session you can do that. I have mentioned that a dielectric is nothing but going to polarize all its molecules in such a way that it creates an induced field inside that material, because of which this induced field opposes the external field, and that reduces the net electric field inside that material. The strength, the dielectric strength of that material is given by the symbol K, if you remember it. So this is nothing but a quick revision. So the moment you have a material of dielectric strength K, the electric field reduces. The electric field reduces because of the induced electric field, because of those polarizations that are going to occur inside that material. So please go ahead and watch that video. I have done that few weeks back. You will find it in the electrostatics and Gauss law playlist. Please do that, all right, if you have not understood that concept of dielectrics. Now we will see what happens when you actually place a dielectric inside a capacitor. Now the moment you place a dielectric inside a capacitor, what happens is, understand, the electric field inside the capacitor will try to reduce, correct? Why will the electric field reduce? Because that's the property of the dielectric material. So the moment you put a dielectric material, the electric field will try to reduce. But understand, the capacitor is still connected to the battery. And if the capacitor is still connected to the battery, that electric field must be formed over there. All right, that electric field must be formed, and the reason for that is, understand, that electric field is nothing but the voltage difference divided by the distance between the plates. So that electric field which is going to be there, that electric field will be nothing but that voltage difference divided by the distance between the plates. You know this formula, delta V by delta R. So if electric field reduces, distance should change or voltage should change, but I know neither of them are changing, because the battery is still the same, the distance between the plates is still the same. So that means if voltage and distance, neither of them are changing, the only possible option is that electric field must remain the same. Now you'll be like, sir, but you have put a dielectric, so how can electric field remain same? The answer to that is the electric field can remain same by accumulating more charges on the plates. So what happens? More and more charge gets accumulated on the plates in order to preserve the electric field. Understand? So that's why a capacitor with a dielectric slab placed inside it, you will see the charge on its plate is more to compensate for the loss in the electric field, and it preserves it by accumulating more and more charge on the plates. I hope this is now clear. Alright, so this is the main concept of a dielectric inside a capacitor. Get this straight. Alright, you can watch this part again to understand it. This is the simplest way of explaining why the capacitance or the charge increases the moment you place a dielectric slab. Now, Faraday did this experiment with capacitors, and he found that whenever you have a capacitor with capacitance C, alright, and you put some material with some dielectric constant K, then the capacitance, so let's say this material has a dielectric constant K, then what happens? The new capacitance C prime, alright, with that dielectric becomes K times of the old C. What is C? C is the capacitance without the dielectric. What is C prime? It's the capacitance with the dielectric. So if you fill it completely, it increases K times. So K over here is nothing but your dielectric strength. Alright, it's a dielectric of that material. For vacuum, it is 1. For paper, wood, etc., it might be 5, 10, 20, etc. For ceramics, it might be 200, 300, 400, etc. Now, this value will be given to you in the exam, so you don't have to sit and by heart all these values. So do not worry about it. Alright, so that will be given to you, or you will have to find it out by other pieces of information given in the problem. So let's get going. Now that you understood it, think about it. For metals, what is the value of the dielectric constant? Come on, think about it. For metals, what do you think the dielectric constant is? Is it 1? Is it infinity? Is it 0? Or do you think it is 2? Alright, come on, think about it. Give it a thought. See which one should be correct. Just go by the definition, you will get the answer, guys. Okay, I hope you have figured out the answer by now. The correct answer, by the way, is infinity. Now I'll be like, sir, why is it infinity? Guys, the reason is very simple. See, the question says for a metal. Now we know that metal is nothing but a conductor. What is the electric field inside a conductor or any metal? It is always 0. So if the electric field is 0, that means the electric field which was coming from outside has been completely cancelled off. It has been completely cancelled off. In fact, there is a formula which says the electric field inside a material is given by outside external or external electric field divided by K. So the dielectric constant basically is put in this formula and it reduces it by 1 by K times. Understand that. So higher the dielectric constant, the field inside reduces it. Understand. So if inside field is 0, what does it mean, guys? This K has to tend towards infinity. Only then the field inside is going to be 0. I hope this is very clear. If there is field coming from outside, there is dielectric constant K. If it is very large, the field inside will be very, very close to 0. And if it is infinity, then it becomes 0. I hope this is very clear. So that's how you get to this question. This formula has been explained in one of my playlists. You can check it out, Electrostatics and Gauss law. I have explained how this formula comes. Alright, now let's go to the next question. Imagine that there is a capacitor of 2 farad and it is connected to a battery of 10 volts. Okay, and there is a dielectric material of constant 50 which is put inside it. So imagine there is a capacitor of some capacitance 2 farad, and then what you do is put a slab inside it of constant 50. What is the new charge? What is the new capacitance? What is the new potential? What is the work done by the battery, and so on and so forth. So let's try to figure this out. So first of all, let's talk about what were the old charges in the old capacitor without the dielectric. Now when the dielectric was not there, the charge inside it, so Q, alright, 1, which is the old one, will be C, which is 2, into V, which is 10, which is nothing but going to be 20 coulombs. This was the old charge. So there will be plus 20 here and minus 20 coulombs of charge over here. The old capacitance was given to us as 2 farad. Now the moment you put a dielectric slab, the new capacitance C2 will be old capacitance multiplied by K times. What is K? 50. So it is going to be 100 farad. That's going to be the capacitance. Now what will be the new charge? Q2. Because I have still connected the battery, the voltage is still preserved. So Q is CV. So C2 into V. C2 is nothing but 100 and voltage is nothing but 10. So this will be nothing but 1000 coulomb. That's quite a charge, but we have to just go by the values of the problem. That's it. So what is the new charge? Done. What is the new capacitance? That is also done. What is the new potential energy? So let's try to calculate the new potential energy. So the new potential energy can be calculated like this. Half into C. C is 100. Okay, into, so if you want, I'll just write it over here. First the formula, half C into V square. So C is nothing but 100 and voltage is still going to be 10 volts. So 10 square. So 100 into 100 guys is 10,000 and divided by 2 is going to give me 5,000 joules. So that much energy is stored inside of it. Very, very interesting problem. Now this is the end of that problem, but let's say I'm a little bit more curious and I want to figure out some more things in this problem, like what was the initial energy stored in it. Let's say I try to figure out what was the initial energy stored in it, and things will get interesting. Oh, we have to also find the work done by the battery. I'll come to it in a bit. Hold on. What is the initial energy stored in it? Half into C, the old C was 20, into V, which is nothing but 10. Oh, sorry, it was not 20, my bad, it was just 2. So half into C into V square. So that is just going to be 100 joules. Just check this out. So if you think about it, the change in the potential energy is U2, which is 5000, minus 100, which is going to be 4900 joules. So that is the change in the potential energy. Now you might think that this change in the potential energy would have come because of the work done by the battery. Let's try to calculate that. How much is the work done by the battery? Now to do that, just one thing. Remember, on this plate earlier there was 20 coulombs of charge. Now the new charge will be, I have just calculated it, it was 1000 coulombs. So on that same plate, it was nothing but 1000 coulomb. This was minus 1000. Now, from 20, it has gone to 1000 guys. So think about it. Think about it. So there is a change in the charge. Now if there is a change in the charge, obviously that charge has to be supplied by the battery. So if you try to calculate what is the work done by the battery, this is what it is going to come out to be. The work done, I'm just going to use up this space, or else I can just remove this for now. The work done by the battery will be the change in the charge. The charge which has been supplied by the battery. Understand, the battery is going to supply how much charge? 1000 minus 20 coulombs. Understand? So 1000 minus 20. I'm keeping it as it is so that you realize this change has been supplied by the battery. Alright? Or else we can just put it as 980 into 10. Now, why into 10? Remember, work done is charge supplied into the voltage difference. What is the charge supplied? This one. What is the voltage? Battery's voltage 10 volts. So that's why this into 10, which is going to give me 9800 joules. Now this is interesting. The change in the potential energy was 4900 joules, but battery has done much larger work. It has done 9800 joules to build up that charge in that capacitor. obvious question in your mind will be, why aren't they equal? The reason why they aren't equal is because some of the energy is lost as heat during the charging process. Where? In the small resistances of those wires. So understand, not all of that energy gets stored in potential energy. A part of it is lost. In fact, a question could have been, how much heat was generated in this process? So the amount of heat generated in this process is 9800 minus 4900, which is going to be again 4900 joules. Understand that. So 4900 joules of heat is generated in the process of just putting that dielectric inside that particular capacitor. I hope this is very clear now. Very good problem. I have done all the head and tail of that problem, guys, so that any kind of question, if it comes in the examination, you will be able to solve it now. So please watch it again in case you feel that any part you felt you need to understand it or you think that it was not so clear. I hope this is clear, guys. Very good problem. Go ahead and smash that like button out there if you have not done it yet, and join Be Enthused if you are not yet subscribed to our channel. Alright, so let's get going to the next question. It's a very similar question, guys. The only change in this question is that now you will see that the battery is not there. So without the battery, so that battery is not there, and now you are putting up the dielectric slab. So what will be the difference in this situation? Let's try this out. So first, let's write down whatever is given to us. There is a capacitor which is charged to 20 coulombs. So same charge as before, 20 coulombs and minus 20 coulombs. This was before. Understand the capacitance is 2 farad. Now you put a new slab over there of constant 50. So the new capacitance obviously is going to be 100 farad. 50 times of 2 is going to be 100 farad. So what will change in this situation when you have not connected a battery from outside? When you do not connect any battery from outside, understand there is no way a charge can be supplied onto the plates. So if no charge can be supplied on the plates of the capacitor, can the charge change? No. In the previous problem, the charge changed only because the battery did some work, supplied some charges. Here, there is no chance of the charge changing. That means, you know, what will remain constant? The charge will remain constant, and here the new charge will be still 20 coulombs and minus 20 coulombs. So what will change? The voltage will change. Correct. C into V should remain understand constant. The charge should remain constant. So the capacitance changes, the voltage will go down. In fact, the voltage will come down 50 times because capacitance has increased 50 times. I hope this is something which you are understanding. So read the question carefully. What is happening? How is it connected? Is the battery connected or not connected? If battery is connected, the voltage difference will remain constant. If battery is not connected, then the charge on the plates will remain constant. That's something which you should keep in your mind. Now, if this is understood, guys, let's go ahead and think what else has been asked. What is the new charge? Yes, I did that. What is the new capacitance? That is also done. What is the new potential energy? Well, let's do this. What's the new potential energy? U2 will be, understand, I won't use half CV square because V is not constant. Instead, I will use half Q square by C. That will be better. The new capacitance, new charge is what I'm going to use. So it will become half. Q is nothing but 20. So 20 square. And the capacitance, guys, capacitance was 100. So 20 square is 400. 400 by 100 is 4. 4 by 2 is nothing but just 2. So it will be 2 joules. That's the new energy stored. What is the new potential difference? Well, you can do that. Since Q2 will be equal to C2 into V2, the new charge was just 20. Capacitance is nothing but 100. And potential difference is what we need to find. So V2, so V2 will be nothing but 20 by 100, which is nothing but 1 by 5 volts. That's the answer. Alright, so understand the voltage has decreased, guys. The voltage has in fact changed only because the charge has to remain conserved. So very, very important problems that you are seeing out here. Okay, so let's get going to the next question coming up on your screen, and here it is. These kind of questions are also very popular, where the slab is not filled inside the capacitor completely. It is partially filled. So let's do this kind of problems, and I'll take some special values so that you get the hang of it. That's all. So let's try this out, guys. So imagine that there is a capacitor and it is partially filled with a dielectric slab of constant K, and let's say it is only being half filled. What you can do is, you can think of it like two capacitors, guys. Yes, you can think of it like two capacitors, where one capacitor has that slab completely filled and another capacitor which has an air gap in between, so that it looks like two capacitors in series, but the area of cross section is the same. So very important technique. If there is a slab filled in this manner with some air gap, treat it like two different capacitors, one where the slab is completely filled and the other one where the slab is not there, so there is just vacuum out there or air. And now these two capacitors are obviously in series because they are one after the other. So what you need to do is, first think about what will be the capacitances of each one of them. So to do that, assume that the area is A, and assume this distance is d by 2 and this distance is also d by 2. Let's just assume, alright, it is exactly half. Alright, exactly half of that width between the plates has been filled by the dielectric slab. Let's just assume that for simplicity. So this new distance, alright, this new distance over here is d by 2. The area is still A. Here also the area is A. Distance is d by 2. So let's think about the capacitances in each situation. So the capacitance of this guy, alright, the capacitance of this guy will be epsilon naught A by D, and D is nothing but D by 2. So it will become 2A epsilon naught by D. That's the capacitance of only this much part. The capacitance of this part, well, you can figure it out. It will be nothing but epsilon naught. Guys, this formula was taught to you in capacitances, alright, lecture 1. So if you have not watched that lecture yet, please go ahead and watch it. The parallel plate capacitance is given by epsilon naught area divided by the distance. That's the formula. Okay, so epsilon naught into area is the same, but this epsilon naught will be into K because there is a slab inside it. So you have to change the permittivity K times. Remember, capacitance increases K times, so do not forget about it. And then divided by nothing but D by 2 again. So this will become 2A epsilon naught K divided by D, of course. Now, once you have understood these two parts, just use the capacitors in series formula. So capacitors in series is given by this formula, 1 by C1 plus 1 by C2. Do not forget it. It is not C1 plus C2. It's not like resistors. It's exactly opposite of that. So just do that. So 1 by C1, matlab, just flip this. So that will be easier. So D by 2A epsilon naught K plus, flip this, D by 2A and epsilon naught. I hope this is fine. And now you can take out few terms common like D, 2A and epsilon naught, and it will be 1 by K plus 1. So what you can do is this can be written down as 1 plus K by K. Alright, so this can be written down as 1 plus K divided by K after taking LCM. Now this was, remember, 1 by CS, so flip it, guys. So CS will be 2A epsilon naught K divided by D into 1 plus K. That should be the answer. 2A epsilon naught K, and denominator will have 1 plus K into D. That's the final answer. That's how you figure it out. If the distance was not D by 2, D by 2, if it was D by 3, 3D by 4 or something like that, you can accordingly change these things and you will accordingly get a different answer. So it depends on the variables being used. I hope you have understood the logic behind this. So now any type of problem like this, if there are two slabs, half is filled with K1, half is filled with K2, you can still do the same problem, just that instead of epsilon naught here, you will have epsilon naught into K2. That's the only difference. So don't sit and bahut formulas, just remember the procedure of solving the problem. I hope this is clear, guys. Okay, so let's get going. Now I'll give you another type of question. Imagine the slab is filled here, not like this. So in the previous question it was filled like this. What if it is filled this way? Okay, what if it is filled in this manner? So the only change that happens, guys, is that, again you divide it into two capacitors, but you can guess this time the capacitors will be in parallel. Correct. So one capacitor will be on the top with the same distance but small area, and the other capacitance will be below. So what will be same will be the voltage difference. That's why they are said to be in parallel. Now same procedure, but again be careful with the variables. Let's assume that this much area is A by 2 and this much total area is A. So the total area is A, this much area is A by 2, and the distance between them is, let's say, D. Alright, that is what is given. So think about it. What will be the capacitance of this guy? Only the one on the top, that capacitor on the top. That will have a capacitance of epsilon naught A by 2 by D. That's it. So epsilon naught A by 2D. That should be the capacitance of the top part. But of the bottom part, what will it be? So think about it. It will be again epsilon naught A by 2 divided by D, but this time there will be a K on the top. Reason, because there is a dielectric slab filled completely inside it, so put that K over there for that particular capacitor. Now capacitance in parallel, the equivalent is given by C1 plus C2. Understand the formulas are exactly opposite to the ones used in resistors. So C1 plus C2, that means C1 is this one, epsilon naught A by 2D, and C2 is nothing but epsilon naught A by 2D, but this time it is K. So therefore that equivalent capacitance will be epsilon naught A by 2D into 1 plus K. So that's a small change in the formula, but this is how the procedure is. So if you have multiple slabs in parallel, now you know what to do and how to solve the problem. Very, very interesting problem. Alright, I hope you have understood this, guys. Take a moment and understand these problems, very important problems, because you guys were asking for dielectric questions and the theory. That's why I have made all these questions which will lay your foundation for solving all the JEE Mains advanced type of questions. Remember that. Alrighty, so let's get going to the next concept, and before that let me tell you, for all the 12th and the dropper students, the crash course launches every Monday. So the details of which are there in the description box below. Go ahead, open that link later on and see all the details, because you're going to get 120 live sessions and 10 full and 10 part test series, along with doubt solving after the class, from morning till night. And during the sessions, it's a two-way interaction where you have the master teacher who is teaching you and also a class teacher who is also helping you with your doubts. And there are lots of test series, test analysis, test discussions, tips and tricks sessions, and so much more. So go ahead, check it out. The course price is, after discounted price, is 8,000 rupees, and the link for joining the course is there in the description box. The coupon code is SHCC. So I'll just write the coupon code out here in case you do not know it. All right, it is SHCC. So that's the coupon code, guys, from which you can get straight away 8,000, the course at 8,000 rupees, straight away 20% off. So use that. All right, so let's get going to the next part of capacitors, that is charging and discharging of capacitors. So get ready, guys, very, very important topic coming up. Now you can see in this circuit what is happening. There is a battery. When the switch is on, all right, so right now it is off, hold on, the switch will be on soon. As soon as it is on, it charges this capacitor, and the moment you turn off the switch, this capacitor drains all its energy across a light, bulb, fan, doesn't matter. It drains all its energy across all the loads and the resistances, and that's it, the energy goes away. And again, when you turn back the switch, again it charges. So this is a charging circuit, this is a discharging circuit, and we are interested how does the charge in a capacitor change with the time. Alright, so that's what we are going to do. Let's get going. Now, I have told you this before that when you just start charging the capacitor, the charges keep flowing in the capacitor, and once the capacitor is charged, no current flows inside the circuit. Understand? So initially there will be a good amount of current flowing, and then you will see the current will go away. Reason is, once the capacitor is charged, there is no further need of charges on the capacitor plates. So if there is no charge which is going to be built up, there is no flow, that means there will be no current once a capacitor is charged. But during the charging process, current will keep flowing. Keep this in mind. Alright, this is very important. So with this, let's see the three important charging diagrams. Now this is something which not many people do inside the class, so I will be doing this. Now, how do you charge a capacitor? Very simple, take a battery, connect the terminals, and it becomes charged. But remember, always there is some kind of resistance. It could be either the internal resistance or the wire resistance, doesn't matter, but there is always some kind of resistance in the circuit. So think about it, when you just start charging the capacitor, look at the time is 0, you have just started. So this is just started the charging. What happens is, the charge on the capacitor is 0. Alright, the charge on the capacitor is 0. This is that resistance, this is that battery. What about the current? Well, I'll come to it in a bit. You will see it's a very interesting value. You can keep guessing, but I'll tell you the value of the current in a bit. Now, what happens is, after some time, when the charges begin to accumulate over the plates, alright, charges begin to accumulate over the plates with the progress of time, there will be some charge Q on the plate, and this is because of the current flowing in this circuit, and this current has been provided by this potential difference created by this battery, of course. After some time, like I said, once the capacitor is completely charged, capital Q. So capital Q tells me the final charge. So right now the charges are just getting accumulated. Eventually it will be completely charged. No more further charge accumulates on it. But that happens after a very long time. That current will be 0. Understand? Eventually the current is going to be 0. So initially the current is there, and slowly the current dies out and eventually becomes 0, because once it is completely charged. So this particular state is called as fully charged. Sometimes it is also called as steady state. So this is also referred to as the steady state. Usually before this, the problems that you had seen were all the ones where the capacitor was fully charged. So you'll be like, sir, but we didn't account for this time where it was charging. What if we have gone wrong? Don't worry. Most of the times, the time taken to charge a capacitor is in few micro or milliseconds. You're going to see the formula. It's going to be extremely small, so you don't really have to worry about it. Okay? So, guys, what is the charge then as a function of time? The charge as a function of time comes out to be CE into 1 minus e to the power minus t by RC. This is the function of the charge we get after integration and when you use KVL. So the way to derive it is using KVL and integration. Kirchhoff's voltage law and then integration gives us this result. The charge as a function of time. Very important formula. You should remember this. E is that value 2.72. Alright. C is the capacitance, E is the EMF, T is the time, R is resistance, C is again the capacitance. This is very important formula. Now let's think about it. Let's think about it. What will happen if I try to find the current? The current will be dq by dt, guys. So it's as good as just differentiating this equation. Now you can try differentiating this equation mentally. It's not that difficult. The derivative of this function will be, this is a constant, so 0 plus, minus CE minus minus has already come, e to the power minus t by rc is derivative. You can try it out. It will be minus 1 by rc. All right, this is chain rule, into e to the power minus t by rc. This is what you're going to get. All right, now minus minus cancels, cc cancels. The current is going to be, think about it, E by R into e to the power minus t by rc. That's the value of the current, guys. Now, interesting thing to note about this current is, if you put the value of time as 0 in this particular function, e raised to 0 will be 1. You will get the current as just E by R. Just E by R, which means that the original current in this circuit, when you just started, that current was just E by R. As if the capacitance is not there. It kind of makes sense because there was no charge on it. The current gets too excited, it flows as if there is no capacitance in the circuit, and that current is just E by R. That's it. Very interesting. So that's the initial current, and you can verify all these formulas by putting special values. How? Put the value of time as 0. If time is 0, e raised to 0 will be 1. So this will become 1. 1 minus 1, 0. So initial charge will be 0. That is correct. Exactly correct. And if you put the value of time as infinity, mentally you can do this. E raised to minus infinity means, e raised to minus infinity, guys, is nothing but 0. Because actually e raised to minus infinity is nothing but 1 by e raised to infinity. And what is this going to be? It's going to tend towards 0. So this entire term will become 0. Hence your answer will become CE. Yes, the answer will become, this Q is just going to be equal to CE. That's the final charge. In fact, this is what you have been using. CV is the final charge inside a capacitor. So that's how you get it. Very interesting formula. Okay, so you can put special values and you can see how this works. Alright, I hope this is clear. Now I'll show you the graph. I've showed you how to manipulate this equation to get current. Now the graph of this function comes out to be like this. Which function? This function. Q is equal to CE into 1 minus e to the power minus t by RC. If you plot the graph, it comes out to be like this. You can see it increases, but the rate at which it is increasing slowly comes down, and eventually it stabilizes after some time. This QF is your final charge CE, guys. This is your final charge, eventual steady state charge after a long time. I hope you understand that. But you can clearly see after some time it almost reaches like 99.9% of the charge. So as soon as it reaches almost 99% of the charge, we can say that the capacitor is almost charged. You're not going to wait for a very long time. So understand, 99 to 99%, 99.9%, you can say almost the capacitor is fully charged. So it's not going to consume a lot of time. If you write it in a slightly different form, and what is the different form? Let me tell you. There is a very important constant which is defined in a charging circuit called as the time constant. So what is this called? This is called as the time constant. And the time constant is basically this value, R into C. R into C. The symbol for that is tau. That same symbol which you use it in torque, the same symbol you use it here. That's the value of something called as the time constant, resistance into capacitance. You can write this beautiful formula like this: QF, final charge, into 1 minus e to the power minus t by tau. This is the formula in the modified form of time constant. Now, what is the advantage of writing it in this form is that if you remember certain values, like imagine E's value is approximately 2.72, but 1 by E's value is approximately 0.37. Okay, 1 by E's value is approximately 0.37. Now think about it. If I put the value of time as RC, you wait for this much amount of time, what will the charge be? It will be Q into 1 minus RC is nothing but tau. So tau by tau will become 1. So it will become, understand, e raised to minus 1. Or if you want, I'll just put it over here, tau by tau. This will become Q into 1 minus 1 by E. 1 by E is 0.37, remember? So it is nothing but Q into 1 minus 0.37. You can by heart that value, is very important. And this will give me 0.63 times of Q. So the charge after one time constant is 63% roughly of the final charge. That's why this value has been shown inside this graph. Understand that. So after one time constant, the charge is 63%. After two times constants, it will be 63% of that remaining value. So if you think about it, 63% of that remaining value. After one more time constant, 63% of that remaining value. So it keeps building up. In fact, within some 2 or rather 3 and 4 time constants, it will be almost fully charged, almost. Okay, so that is something you should remember. Very, very important values. So you should know the formula for time constant. You should know how to write the given equation in the form of time constant. And you should know that after one time constant, the charge on that capacitor is 63% of the final charge. Remember this. All right. Now, if this is understood, let us talk about, the final conclusion of charging. Then I'll go to discharging. Remember, when a capacitor is just connected to a resistor, okay, and when a capacitor is completely charged, it behaves very, very differently. So understand, when a capacitor is completely charged, there is no flow of current through it. So you can treat that capacitor as just like an open switch. So a capacitor which is completely charged, where no current is flowing, that can be treated like an open switch. So you can just replace it with this diagram. And I have given this to you in my previous session. Now I'll add something more to this. If a capacitor is just connected, it's not even charged right now. If you just connect it, then understand it allows the flow of charge, and this capacitor behaves like a wire. It just behaves like a simple wire because it allows full passage of current and it has not yet been charged. It does not oppose anything. So it just acts like a closed switch. Very, very important slide. A fully charged capacitor is an open switch. An uncharged capacitor is like a closed switch. Very, very important. So write this down. I hope you are making your notes. Okay, and remember guys, you always get all these notes even in the form of extracts. So at the end of every chapter, in the description box and in the Telegram group, you will be getting all the formulas, important pointers in the form of the summary of the chapter, which you can use it to make your own notes. Please do not just use it ready-made. You have to use it in your notes and make your notes. All right, that's very important. All right, now let's talk about discharging of capacitors. So when you connect a capacitor which is charged to a battery, all right, the switch was open, now you close it, all the charges are going to drain out and they will be used up against some work done. Some heat will be produced, some light will be there, some fan will rotate, anything. So when a charged capacitor is connected across a bulb, fan, motor, anything, all the charges will get utilized, all the energy will get utilized, the charges will flow, and the current will be used for doing some kind of work. So that is how you discharge a capacitor. Very simple. So what's the different stages? What are the different stages of discharging a capacitor? Again, let's start from the beginning. You take a capacitor which is completely charged. So this is a completely charged capacitor. So the capacitance will be C, the resistance is R, and the charge initially is plus Q, let's say, and here minus Q. So the capacitor has lot of charges over here. Now the moment the circuit is complete, the charges will begin to flow, the charges will decrease. At some time the charges will be, let's say, small q. There is some current flowing in this across this resistor. Slowly you will see all the positive charges will go here and it will nullify these negative charges till after a long time you will see there will be no charge on the capacitor. This is fully discharged. This is going to happen after a long time. This is a fully discharged capacitor. So what is the charge as a function of time? This is the function. Q is equal to initial charge e to the power minus t by RC. Very similar, but just the only difference is instead of 1 minus e, it is just e. That's the only difference. So this is the formula that you are supposed to remember. Remember, this is the initial charge on the capacitor. And if you are interested in the current, just differentiate this. So if I am interested in the magnitude of the current, just take dq by dt, which will be nothing but q into derivative of this will be minus 1 by RC into e to the power minus t by RC. That is using chain rule. You should be very well familiar with this, all right? And because we are only interested in the magnitude, so that minus sign can be forgotten and it will become q by RC into e to the power minus t by RC. So very, very important formula again. So this will be the current flowing in the circuit at any time. You can just get it by differentiating it. So if you are very good at derivatives, you won't even by heart this formula, you will always end up differentiating it. And I feel that is what you should do. Always differentiate it rather than remembering thousands of formulas. It's very simple. It will take you hardly 5 seconds. Okay? So that's how you do this. Now, what will the charge look like as a function of time? It will slowly decrease till it eventually becomes 0. So this is how the function looks like. And again, I can define time constant as RC. So my equation will look like initial charge into e to the power t. Instead of RC, you put tau, that time constant. This is in the form of time constant, and you can see as time progresses, oh, there was a minus sign there. Yeah. So you will see as time progresses, okay, as t increases, you will see e to the power minus t will decrease, and that's why q will decrease. So because it's a negative part, so it will keep decreasing. And if you put a special value, t is equal to RC, which is just tau, the value of charge that you will get will be q into e to the power minus tau by tau, which is q into e raised to minus 1, which is 1 by e. Remember what was the value of 1 by e? It was 0.37. So it will become 0.37 q. Very important. That means the final charge after tau seconds will be just 37% of the original charge. So you can see it has basically discharged 63%. 63% has been discharged. Only 37% approximately is remaining inside the capacitor. Very, very important problem. All right, you can note it down. Now let's get to some problem solving. Here's your first question on charging and discharging of capacitors. So there is a capacitor which is connected to a battery, and there are two switches like shown over here, S1 and S2. The resistors are R1 and R2. The capacitor will have maximum charge. So this capacitor will have maximum charge when? Which of the following situations do you think the capacitor will have maximum charge? Come on guys, think about it. Both the switches are given over here. When do you think it will have maximum charge stored on it? Come on, it's very simple. I hope you have made up your mind by now. Come on. Well, let me reveal the answer to you. So the correct answer, guys, come on, guess. Put it up in the chat box. Come on, discuss among yourselves. Keep the enthu up. The correct answer, by the way, is option B. Now, why is it option B? Let me tell you. See, guys, forget the capacitor for a moment. Just forget the capacitor for a moment. Just assume both the switches are closed. Obviously, both can't be open. Then there will be no charge only on the capacitor. So then, imagine this battery is of 10 volts. Just example. So, if this point is 0 volts, this point will be 10 volts. It's best to do using example, then you will understand it clearly. Now, if this is 0 volt, even this point is 0 volt because this is the same wire and this is also 0 volt. Correct? You can mark the potentials very easily. Now, if this is 10, that is 0, this will be somewhere in between. I don't know how much it is, but it will be somewhere in between. I don't know. I'm just going to say that, it's going to have, let's say, 2 volts or 4 volts or something like that. So, there is a potential drop of 2 volts across this capacitor. I hope you can see that. Very easily, you can see that there is a potential drop of 2 volts around this capacitor when both the switches are closed. Now, keep this in mind. Now, the question was the capacitor will have maximum charge. Obviously, the charge will be maximum when the voltage drop across the capacitor is maximum. So, right now the voltage drop is 2 volts. So, proportionately the charge will be proportional to the 2 volts. Now, just imagine the next situation where this switch is closed, this switch is open. If this switch is closed, that switch is open, then what will happen? If this is 0 volts, if this is 10 volts, if this is a 10 volt battery assuming, then this is also 0 volt. But then what will be the voltage of this point? How do you know? You won't know it because you do not know what is the charge stored in the capacitor, right? But think again guys, because in this branch of the circuit, alright, there is no current flowing. If there is no current flowing, why? Because the capacitor will block the current completely. If the capacitor is going to block the current completely, then there will be no voltage drop across this resistor because the current is 0. IR will be 0, so voltage drop is 0. If there is more voltage drop, that means what will happen, guys? Think about it. If there is no voltage drop, that means if this point is 10 volts, even this point will be 10 volts. Interesting. Now, the voltage drop across the capacitor is maximum. It is 10 volts. In the previous situation, when both of them were closed, it was lesser than 10. So, hence, S1 should be closed and S2 should be open. That's when the charge will be maximum. What a brilliant question, I would say. Very good question. Alright. Now, there is another part of this question. It says, same circuit is given, but the question is when both of them are open initially. Now, what will be the current when S1 is just closed? So, what will be the current through the battery? Only S1 is closed, S2 is kept open. Now, when you just close this switch over here and this switch is open, just focus your attention only on this part of the circuit. What did I tell you just some time back? When you just connect a capacitor which is uncharged, this capacitor behaves like a wire, closed switch. I have told you this just some time back. So whenever there is an uncharged capacitor just connected in the circuit, it behaves like a wire or just a closed switch. But a charged capacitor behaves like a blocked circuit, like the one we just did before, or open switch. So this is as good as saying you have a circuit where there is a battery and there is a resistor. That switch is of course closed, and there is another switch which is again closed over here, and that's about it. Nothing else apart from that. Nothing else apart from that. So guys, this capacitor has been converted into a closed switch. So what will be the current? Obviously the current will be EMF divided by resistance. That's the current which will be flowing initially. After that, the current is going to definitely change. So these are very brilliant questions based on this concept which I just told you just some time back. This one. A charged capacitor is an open circuit. An uncharged capacitor initially behaves like a closed switch. That is something which you should remember. This is something what I told you. Now let's go to the next question. Very interesting question coming up. In a RC series circuit, the battery voltage is 12, resistance is 1.4 mega ohm, capacitance is 1.8 microfarad. Question is find the time constant, find the maximum charge, and also find how long does it take to build up half the initial charge. So first let's visualize what is exactly happening. So in this problem, you just have one capacitor, a resistor, and think of, just one sec. So you have a capacitor, you have a resistor, and there is a switch which is just closed, all right, and you have one battery. The resistance is 1.4 mega ohm, the capacitance is 1.8 microfarad, and the battery voltage is 12 volts. So obviously some charge is going to be built up on it. So this charge, obviously we know, will be a function of time as you close that switch. So the first question is, what is the time constant? Well, time constant is just RC, that's plain simple. R is how much? It's 1.4 mega is 10 to the power 6, and C, capacitance is 1.8 microfarad, guys. So 1.8 into 10 to the power minus 6. Just check this out. Hence, these two will get cancelled, and what will you have? You will have 2.52, but this will be in seconds. So what does this value tell me? This value tells me in 2.52 seconds, the charge on the capacitor will be 63% of the final charge. Remember one time constant? So 2.52 seconds, it will be almost 63% charge. You made for some more seconds, it will be almost 99.99% charged. Okay, that's the first answer. So what will be the maximum charge that will appear on the capacitor? The final charge, Q final, is just CV or CE. That's it. C is nothing but 1.8 micro, means 10 to the power minus 6 farad, and voltage is nothing but 12. So come on guys, what will be the answer? It should be 21.6, but this will be micro coulomb because of the 10 to the power minus 6. So that is your final charge on the capacitor eventually. That's the second answer. Last question. How much time does it take to build up half the final charge? So for this, I will use the mathematical function, guys. Remember, Q was final charge, okay, into e to the, or rather 1 minus e to the power, okay, minus t by RC or tau. This was the equation that I told you just some time back. So this Q is half the final charge that is there on it. So hence this will be half of capital Q is equal to Q into 1 minus e to the power t by tau. Now let's rearrange this. So Q will get cancelled, this will become half, correct? Now shift this term e to the power, oh there was a minus sign, e to the power minus t by tau on this side and take that half on the other side. So it will become e to the power minus t by tau, correct, will be 1 minus half. 1 minus half is just half, that's e to the power minus something. So take the reciprocal, so e to the power t by tau, correct, will be just 2. So I just taken reciprocals guys, that's all. Now if this is the scenario, use the definition of logarithms and you will get ln2 is equal to, ln2 will be equal to t by tau. Tau is the time constant. Now just shuffle it. T will be equal to ln2 multiplied by tau. And I know both the values. ln2's value is 0.693 and tau, I just figured it out, it was 2.52 seconds. So just multiply them and see what you get. Obviously the answer should be less than this time because for this time it charges to 63%. So the answer to this question should be less than that. What will it come out to be? Come on. I think it comes out close to around 1.75 seconds. Just check that out. Alright, so it will come out to be around 1.75 seconds. That's the answer to the final question. Very, very interesting. So this is how you have to solve problems guys on charging of capacitor. Let's do one final question today. Again you have a capacitor with some energy stored in it and it is discharged through a resistor. Find initial charge, find the current when the discharge just begins. Very, very interesting question. So let's do this. So essentially what you have is a capacitor which gets discharged when the switch is just closed. The capacitance is 1 microfarad and the resistance is 1 mega ohm. That's what is given. And initially there was some charge on it, but that charge will obviously go away. Once you connect that switch, you will see all this charge is going to go away and it is going to nullify it. Now the first part, what is the initial charge? So for that I can directly use the formula guys. U is equal to Q square by 2C. This is the formula for energy stored inside the capacitor. The value of U is how much? It is 0.5. What is the value of Q guys? Q. Oh, that's what I need to find. So it is Q square. 2 into capacitance. What is the capacitance? It is 1 microfarad. That means 10 to the power minus 6. 2 into 0.5 is 1. So Q square will become 10 to the power minus 6. Therefore, Q will become just 10 to the power minus 3, but that is coulomb, which is nothing but 1 millicoulomb. That's the answer to the first part of the question. Alright, so that's the answer guys. Now, the question is, what is the current through the resistor when the discharge just begins? When the discharge just begins, what is the current flowing through it? Now go back to the original equation of charge as a function of time. For a discharging capacitor, it was Q into e to the power minus t by RC. Now when you differentiate this, I just done that sometime back, dq by dt, you will get the magnitude. Alright, so I'm interested more in the magnitude. You will get Q into, alright, minus 1 by RC into e to the power minus t by RC. Because derivative of e raised to x is e raised to x, and when you use chain rule, these terms come below over here. Now when you take the mod value of that, so the current will come out to be Q divided by RC into e to the power minus t by RC. But the question says initially, what is the current through the resistor when the discharge just begins? That means, think about it, the value of time that you're going to put will be 0 initially. So just substitute all the values. The initial charge is 1 millicoulomb, that means 10 to the power minus 3. The resistance is 1 mega ohm, that means 10 to the power 6. And the capacitance is nothing but 1 microfarad, that means 10 to the power minus 6. These two go, and the current will come out to be 10 to the power minus 3 amperes, which is as good as 1 milliampere. So that's the magnitude of the current that will be flowing initially. There can be more type of questions on this, like how much energy is lost across the resistor. This can be also a question. If that question is asked, then all you need to do is just look at the initial energy stored. How much energy was stored? 0.5 joules. Whatever was stored will be completely lost as heat, so that will be the answer. Okay, so you don't have to sit and integrate anything. It's just the initial energy stored will be lost because there is nowhere else it can go. So these are some typical questions that you get in charging and discharging. The main thing is you should be good with derivatives and integration. Then you can solve these problems really quick, else you'll be struggling in those derivatives and integration, guys. So check out the integration derivatives lectures in the math section as well. So that will be very helpful. So this is your homework question. So there are 3 dielectrics. The sizes are mentioned very clearly. These are the 2 plates, and between these 2 plates you have placed these dielectrics. So the question is, find the capacitance, find the total capacitance between the 2 plates. Very interesting question. Take a screenshot of this, all right, and post it up in the comment box below, and you will be getting all the solutions on our official Telegram group. So very important, join the Telegram group. The link is in the description box below. And guys, stay tuned, keep coming more often. Do not lose focus. What is very important, that you should stay focused and be consistent. So after this capacitors, I'm going to start with magnetism, and that is going to be again a lot of fun. And slowly we are going to reach towards the end of the 12th standard portion, guys. Because after magnetism you will have electromagnetic induction, and then little bit of modern physics, and that's about it. And we are going to have lot of problem solving sessions, KVPY sessions, so many things that are coming up planned for all of you. And also the crash course is there. If you want more practice, more test papers, and you want assignments, etc., the crash course is also available. It's at a discounted price of 8,000 rupees. All right, so go ahead, join it, and the discount coupon code for that is nothing but SHCC. To get that offer of 20% off, use the discount coupon SHCC. That's very important. All right, so bye bye guys, take care, have a great time, and do not forget to hit the like button down there. Come on, do it if you've not done it yet. And if you're a new member, if you want to get more updates, more videos, etc., please go ahead, hit the subscribe button down there. Bye bye guys, take care. This was Shreyas here, your master teacher.